Alrighty, everybody. Welcome to 7.5, Congruent Triangles to the Rescue. So, we're back with Zach and Sinoe. Sinoe? I don't know how to pronounce that. Sinoe. Anyway, they're exploring isosceles triangles, and we're going to kind of walk through their story together. They're exploring isosceles triangles in which two sides are congruent. Zach says, I think every isosceles triangle has a line of symmetry that can pass through the vertex point of the angle by making up two congruent sides and the midpoint of the third side. Sinoe, I don't know. That's a pretty big, I'm going to change the name to Simon because I can't read that. It's a pretty big claim. You say you know something about every isosceles triangle. Maybe you just haven't thought about the ones for which it isn't true. But I've folded a lot of isosceles triangles in half and it seems to work. Well, lots of isosceles triangles are not all isosceles triangles, so I'm still not sure. What do you think about Zach's claim? Do you think every isosceles triangle has a line of symmetry? If so, what convinces you this is true? If not, what concerns do you have about his statement? I might agree with him because it seems like a lot do, but I think Simon is right. He definitely just testing lots doesn't mean you've tested everything. So we can't really say that he can make a claim. What he has is experimentation. He's experimented on a bunch of different triangles, and even though it's been lots, he could have even done 100, 200, 300 triangles, but he still hasn't found the one that it doesn't work for, right? You can't physically test all triangles. And so that's a problem, right? We need to come up with something a little stronger than just, oh, I tried a bunch of them. What else would Zach need to know about the crease line in order to know that it is a line of symmetry? Well, a line of symmetry, think about that. It is exactly symmetrical on both sides. It is exactly cut in half. We would need to know that that's perpendicular. We need to know that that line, that crease line, is perpendicular. If it's not perpendicular, then it's not actually a line of symmetry. So let's kind of draw this little picture over here, best I can. Here's an isosceles triangle, right? He's claiming that if I draw the crease line down the middle, well, his crease line could be like my line and just kind of off, on the side here. We need to know that that is a perpendicular line. If that's a perpendicular line, then we truly have a flip over. Simon's thinking Zach's crease line, a line folded by forming isosceles triangles in half, creates two congruent triangles inside the isosceles triangle. Which criteria, angle, side, or side, side, can he use to support this claim? Describe the sides or angles you think are congruent and explain how you know they are congruent. Okay, we have to be careful about this. Our picture may look like we know something, but it actually has to be stated on the page. So let's state some things that we are guaranteed to be true. Well, let's label it. We'll do A, B, C. Here's our big triangle. We can say that angle A is, we can't say anything about angle A. We don't know anything about angle A. We can say that side AB is congruent to side BC. That is a given piece of information on the page. That is due to the fact, we'll put a little like because, it is isosceles. Because it is isosceles, whoops, forgot these. Because it is isosceles, we have a bigger reason than just it looks like it. We can say those two sides are congruent. Okay, so far we're at a side. Well, all three cases have sides, so that doesn't really help me. All right, what else we got? We got that, we're gonna have to label this point D, right? Because we got two different triangles. Angle ADB congruent to angle CDB because of that fold line, because it is actually perpendicular, because they're both 90 degrees. Okay, alrighty. Well, actually, can we say that? We just said that he doesn't know that they're 90 degrees. So actually, we can't say that. Just kidding. Let's cross that out. Notice we're kind of messing around with this. That's a good thing. I'm doing this intentionally. All right, what do we know? We don't know anything yet about the degree length. Well, I can at least say that this side's the same, right? Because they are the same side. So DB congruent to DB. There's really no way to mess that up. Then I can say the same side. Okay. So it's obviously not this case because we need two sides. We have two sides that are the same. Well, we don't know it's 90 degrees, but we do know that these two sides are congruent now because at least that's a midpoint, right? At least that's a midpoint in between these two. Thus, I have created two different midpoints. And so we can say that AD congruent to DC. Oh, it's side, side, side. This one was by midpoint. And we have three very strong reasons to say something. This one, I thought I knew that, but I cut it out because that was just a guess. That was something we needed to know, right? And I didn't know that yet, so I couldn't say those were 90 degrees. But now I can say they are the same. These two triangles on here, we can say that triangle ADB is congruent to triangle DCB. ADB, no. Triangle CDB. Right, this one congruent to that one. All right, cool, cool. If two triangles created by folding an isosceles triangle in half are congruent, what does that imply about the base angles of the isosceles triangle? So let's kind of redraw ABD nonsense over here. Got these two things now. What does that imply about the base angles of the isosceles triangles? The angles that are not formed by the two congruent sides. I think they mean, well, all of the angles we can argue are equivalent now. But these two guys right here, we can argue that those are the same now. So these guys, the angles are congruent because the triangles are congruent. But all of the angles are congruent, right? We can just say that what I was saying before, angle ADB is now congruent to angle, pardon me, not triangle, CDB. Cool. And those are the base angles of the triangle. Alrighty, moving right along. If two triangles created by folding an isosceles triangle are congruent, what is implied about the crease line? Okay, so once again we have our picture. Here's that crease line. We know these are the same. We now know, oops, pardon me. They're matched. Okay, we know that this is the baseline angle. We know that these angles are the same. In order for those angles to be the same, they're giving us the same line. Those angles are the same line. This is perfectly split in between. This must be 90 degrees. It must be a perpendicular line. It must be the case that if two of the same exact line are created out of the same exact angle, we get 90 degrees there. And so we've actually proven that it's 90 degrees. Proved. Much better than Zach's, well, I tried a bunch of them, right? So we actually prove that when you fold the line in half, if it's perfect, you actually get 90-degree angles. Okay, cool. So there is a line of symmetry there. There's a line of symmetry that forms a perpendicular line. What we've just done is called a proof. Nowhere in here did we say it looks like that because we think we know, right? We said we need to know that this line is perpendicular. It's kind of like the claim. And then within that, we've used actual physical theories. We've used actual information that we were able to derive out of these congruent triangles. And we've proved that that was 90 degrees. These guys have to give us the same angle because they are congruent. To give us the same angle on the same side, we get 90 degrees. We have to have a line of symmetry there. All right, let's do kind of the same idea with a rhombus now. Kind of keep going with Zach and Simon's story. Sorry about not being able to pronounce that. Like Zach, you've done some experimenting with lines of symmetry as well as rotational symmetry. In the task Symmetries of Quadrilaterals and Quadrilaterals Beyond Definition, you made some observations about side, angles, and diagonals of various types of quadrilaterals based on your experiments and knowledge of transformations. Many of these observations can be further justified based on looking for congruent triangles and their corresponding parts, just as Zach and Simon did in their work for isosceles triangles. Pick one of the following shapes to explore. We're going to go ahead and pick a rhombus. Draw an example of your selected quadrilateral with all of its diagonals. Label the vertices of the quadrilateral A, B, C, D, and label the points of intersection of the two diagonals at point N. Okay. I'm going to put rectangle and square in kind of the key for this as well if you want to look at those. But we're just going to do a rhombus. Okay, I'm just going to borrow my compass so I can get a nice straight edge. I'm going to draw this on the back. Nice and big. I'm actually going to construct a rhombus real fast. Okay. Call this A, B, C. How do you construct a rhombus? Take this, you measure this length. That's parallelogram. Oh, this is not a rhombus. Just kidding. Let me create a rhombus. We'll create it out of AB. I was making a parallelogram. Silly me. Okay. This is right. I don't recommend a pen. Make that C. Then we take that same one. Nope. Okay. Go to C. That wasn't right. Close enough. Jeez. Okay. And we have our rhombus. You see pens suck. Okay, so here's a rhombus. Right, we got all four sides the same. Looking good. Okay, so now, based on your drawing, give the definition of your quadrilateral and the information about sides and angles that you gather based on... Oh, I'm sorry. We didn't do the label your intersections. Sorry. Okay, so label all of your diagonals. So here's the diagonal. Here's diagonal. Here's the intersection point N. Okay, cool. Let's switch to a different pen color so we can kind of see what we're talking about. So we've got N. I labeled those. I know that from constructions, but okay, so by definition, given the given definition of your quadrilateral is the rhombus, by definition, has all same sides. That's it, right? Nothing else is a guarantee. We don't have the same angles. We don't have anything else about it. Information about your sides and angles that you gather based on the reflections and rotations of symmetries. List as many congruent triangle parts as you can find. Okay. Let's see, we've got a couple triangles in here. We've got the, pardon me. Yep, these sides are all the same. So, congruent parts of triangles, label this D. I'm going to kind of just draw over here some other triangles that I'm seeing. I'm not making this super accurate, I'm just drawing kind of the split. Based on that middle BD line, I'm noticing that if I split this triangle, whoops, it's okay. If I split this triangle, I'm just trying to make this kind of accurate. A, B, D, B, D, C. I can see that BD is going to be congruent to BD, right? That's just given fact. I can see that AB congruent to, since they're all the same, I can say that's congruent to BC. And I can say that AD congruent to CD. And so by side, 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 I can say triangle ABD congruent to triangle CBD. Yeah? Okay. So I got that one. I think I have another case where I could go the other way. I can do kind of like other guy here. Kind of across the other diagonal. And this is A, C, here's D and B. Kind of like the same idea. I've got AC congruent to AC, because duh. I've got, oops. All those same sides. AB congruent, in this case, to AD is the most helpful. And CB congruent to CD. And again, by side, 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 I see that triangle ABC congruent to triangle ADC. Two different triangles, right? Two different diagonals, but we get that those triangles are the same. Okay, we can see that A and C are congruent, and then we can say that because it's the same, because they're isosceles, we can say B and D are congruent, and D and B are congruent. Now, why am I doing it this way? You're going to see in just a second. But basically, we can say that all the angles, the A and C are congruent. And then I can say that B is congruent to D in both aspects. So like this B and that D. So I'll say B1 and B2. We'll say 2 and 3. So you know what I mean. So like the 2's match up, the 3's match up. Kind of get the same case over here. We can see that obviously B and D are the same. And then we get kind of an A1 matching with a C1. I don't know, we'll label this one 4 and 4. And then we get this one 5. So angle A5, angle C5, and then angle A6, angle C6. And I'm just using these because, you know, this is kind of 2 different angles at this point. We could use the system of a BAC, but then there's also like 2, well, I guess there's only one BAC, but we could use that system as well. I just like this number system. Okay, so now if we go back into our triangle here, this number guy is going to help us see something pretty clearly. So angle 1 is right here. Let me use a different color so we can see. Hold on one second. Green. Here's angle 1 to angle 1. Not super exciting there. But let's look at 2 to 2 and 3 to 3. Okay, so that's interesting across the parallelogram, the rhombus there. And then we get 5 to 5, 6 to 6, and then once again we kind of get 4 and 4, which aren't super interesting. But we can see how kind of all of these corners that are created by the diagonals, we get this alternate setup. And so what we can see is not just these triangles, but these guys. We can start to see these triangles. So I'm going to go up here now. Kind of break it into 4 pieces. Not super accurate on these pictures, sorry, but I'm just going for a moot point here, or a point here. We can kind of see that 6, 3, 3, 6. We get 2, 5, 5, 2, and then of course all of these are the same size. Now I'm not claiming that 6 and 5 have anything to do with each other, right? We don't know much about that, but we can see that we get these 2 triangles by angle side angle. We get those are congruent. Same thing here by angle side angle, and so both by angle side angle we can see that, let's see, let's put the letters back in, ends in the middle, B and C. We can see triangle ANB is congruent to its polar opposite, BNC, and triangle ANB is congruent to its polar, oops, that's a D, sorry. Its polar opposite, DNC. And we get that opposite triangles are congruent, which is actually going to lead us to a couple facts about rhombuses next year as well. But something about alternate interior angles, if you've ever heard of that, proving things to be squares. We can kind of keep going with this idea. But for triangle congruency, kind of 2 cases of this rhombus, which is not in itself a triangle, but has 1, 2, 3, 4, 5, 6, 7, 8 different triangles in it, we can prove a lot of these different angles true, just based off the fact that rhombus has 4 equal sides. All right, cool. Kind of the same level with square and rectangles, so I'm going to kind of just leave a key for that one, but this is basically a proof, and proofs can get really complicated really fast if you have no idea where you're going. But this is just an exploration of these either. We don't really have a set, like, something that we're looking for. Proofs is probably one of the hardest things you'll ever see. Super fun fact. All right, if you have any questions, the second half of this page, this task, was just this in like line form. It's kind of how we organize a proof. I'm not super concerned with that, to be honest. Nobody uses that. They kind of do stuff like this, and then they make claims. These are kind of what it would be in our boxes. I think it's easier to see in pictures. So this is proofs. If you have any questions, ask the sub. Otherwise, I'll see you next time for 7.6.